All right, welcome back for part 2 of today. So the first part here now was to establish the condensation equation, right? And so we were thinking about, just before the break, how does a size distribution change its shape if it's subjected to a condensation process? And so we left it a little bit open, actually quite open, what the gas is, right? So it could be whatever, sulfuric acid or some organic that condenses on it, or something we want to focus on a little bit more, just water vapor, right? So droplets growing, or your tiny aerosol solution droplets growing by water vapor diffusion and eventually forming cloud droplets. I wanted to say something else before we jump into this. Yeah, okay. Tying back to what we discussed yesterday, right? So if you think about size distributions and a size distribution that undergoes coagulation. Actually, I wanted to ask you this yesterday, but then we ran out of time. What does that look like? Let's think about this a little bit. Again, here's our diameter, dp, our n of dp. Start out with a size distribution that looks like this. We talked about the condensation. Now let's circle back to just coagulation, right? So how does this size distribution evolve as coagulation? Coagulation between all the particles in that size distribution acts on it. Let's take a couple of minutes or so, each of you, and then try to see what you come up with. And you can talk to your neighbor. Mm-hmm.
So I'm confused with the meaning of coagulation.
Okay.
Because then there's like surface growth, aggregation. How would you define it?
Okay, so coagulation is just two particles stick together.
Okay, and isn't that like same?
It's the same as aggregation, yeah.
Okay.
Different fields use different words for that.
Like in combustion, they use the aggregation.
They just use aggregation. Yeah, I don't know why that is, honestly. Like, why? It must have been evolving historically. And in cloud physics, they sometimes would call this coalescence, collision coalescence, right? Because the particles coalesce together, versus in aerosol science and also in combustion, not necessarily, right? If you have a soot particle, they're solid, so they don't coalesce. So that's yet another different way of saying it. But yeah. So just think about your little spherical particles, and they stick together. That's what we call coagulation, forming a bigger one. And then we do often assume that the newly formed particle, because oftentimes it's little solution droplets, they will become a new spherical particle, slightly bigger. Does this help?
My other question is like coagulation in sampling. It's like makes things difficult. Like when we use the SMPS, we try to insert it in the flame to see the size distribution.
Yeah.
But the sampling line, there's a temperature difference due to coagulation.
Right.
Over time, like this size distribution will start shifting
Yes.
towards larger particles.
Uh-huh.
And we have to like increase the dilution ratio
To
as much as
avoid
possible.
coagulation, yes.
Because the temperature difference is huge.
Yeah.
To SMPS and before.
Yeah, you are exactly right. Yeah, that's how it is. Mm-hmm.
The small ones will like agglomerate.
You ask $1 million questions here, like. Yeah. So for now, we just want to have a little example, like how does this size distribution change when you have coagulation?
So thinking something along the lines of you're going to get like doubling in particle sizes roughly as the individual particles combine.
Are you?
Kind of that was my assumption, but I guess I don't know if that's
No.
no.
Well, think about these are little solution droplets, right? And so you get 1 and 2, they stick together, and then they form.
Okay, yeah. So
Then it's not.
doubling in volume.
Yeah, doubling in volume. Yeah. Okay. So there are a few important assumptions here that I make in my head and you may not make in your head because you're coming from a different field. So let's assume these are actually little liquid droplets, a solution out of, let's say, ammonium sulfate, some salt, or sodium chloride, and they have water in them, and then now they coagulate, right? And so what will happen is you have 2 smaller particles, they bump together, they form a bigger one, but it's going to coalesce and form a nice spherical new particle, right? Not one of these aggregates when you have 2 solid particles and then you form this crazy shaped aggregate. None of this. Let's work with nice liquid little droplets that form nice spherical new particles after they collide. What's your size distribution looking like? Have you been working on it?
We didn't draw it, but I've done that more.
You worked on it in your head? What?
You can draw it. We can draw. We can draw.
Yeah, draw it.
We were just like, it's fused to the right.
I want to have a bit more detail. It's not just going to the right. I see the initial. Good job. Nice. Symmetrical. So what happens next? Which one? Think about who coagulates with who. Which rates? Remember yesterday we said like which ones are preferred in terms of coagulation? Like is it which combination in terms of sizes?
Bigger ones go with small ones.
Yeah, small or the other way around. Smaller ones go with bigger ones. They attach to the bigger ones. Yeah.
So is it? It would shift like that.
Yeah, getting there. So the small ones go away, right? Think about the area underneath the curve.
Well, the number goes down,
Number goes down, yeah.
so it should be shorter.
It should go down, yeah. So that would be quite a dramatic shift, right? So actually the big ones, they don't grow as much. If you think about it, like, yeah, so this is getting there. So in fact, you have never seen this, but the right-hand side doesn't almost change. It's just that the small ones get depleted, right? Yeah, so
So it stays like that.
pretty much, yeah. Yeah, that's what happens. You haven't done it yet? So what's going on here? You don't know how to draw?
So down, I think it's like a fat tail like that.
I want to look at the...
So blue is the original. We're thinking purple is the next. So it shifts to the right.
It shifts to the right.
And then he gets lower, gets wider,
gets
and
lower.
skews.
Yeah.
the fat tail. That's
Okay.
what we're thinking.
All right. Yes, I'm seeing. Yeah. You're not sure. Okay. Let's compare notes. So I'm hearing lots of good ideas here. So what are the ideas? So one of the ideas is, okay, so the total area here we said, right, this is the total number concentration. And when we have coagulation, that number concentration decreases, right? So the area has to get smaller as we go on. So one of the key facts is N total is going to decrease. And then you were also telling me the small ones the collision or the coagulation events between small and large are most preferred, right? The small ones coagulate really readily with the big ones, so they get swept up by the big ones. So the small ones should get depleted. So on the left-hand side, we should see like a decrease in number concentration. And then you were saying they're growing, right? It shifts to the right. And I agree with you, in principle, that is the case. But what happens is, and something I didn't note down, so oftentimes, most of the time, we would actually draw this x-axis logarithmically, right, on a log scale. And if you think about it, if a big particle collides with many, many small ones, to double the diameter, it has to collide with crazy many small ones, right? It takes a lot of collisions to really increase the large diameters. So in these kind of like size distribution plots, you wouldn't see a growth of the big ones like as this huge shift to the right. It's almost, if you look at the plot, almost invisible. But it's definitely true that the small ones get depleted, right? So you get something like this. I should have brought a plot from one of our simulations, actually, now that I think of it, but you get the idea, right? So the area here decreases, and we get like a little growth on the right-hand side, but it's not very visible for the reasons I mentioned, but we are depleting the small ones very efficiently. Yeah, and so you shared how much of a pain coagulation is in your experiment, because it happens in the line, right? Like when you put your sample to the SMPS, is that what happens?
Yeah, if like the dilution ratio is not high enough over time, this size distribution due to coagulation keeps shifting.
Mm-hmm. Yeah. So and often the people I work with, when they have these chambers where they put in aerosols and they want to, for example, investigate a certain reaction, or how a certain secondary organic aerosol type forms. They also try to suppress coagulation because it messes with the size distribution and the number concentration. And so the way to do this is to look at low concentrations, right? Because when you have low concentrations, the coagulation rates are typically negligible on the time scale that you perform the experiment. And if you have really high concentration, then you see like a really quick evolution, which is why we said yesterday, if you look at a busy road where you have lots of emissions from cars, and you look at the ultra-fine particles, those are evolving due to coagulation a lot, compared to when you look at a very diluted aerosol sample far away from the sources, then you don't need to worry about coagulation. All right, so that ties nicely together, what happens on the particle level and how does this get manifested, or how it manifests itself in the size distribution, which is often what we measure. Okay. Yeah. So now for the next segment here, let's look at the growth of particles due to water condensation. And so that is very relevant in our field because aerosol particles are the seeds for cloud droplets, and then the cloud droplets, how does it actually work? How does an aerosol become a cloud droplet, right? So that's the question that we want to answer here. And just to sort of like put as a reminder this equation, our growth equation here. So now for this example, the gas I is water vapor, right? Okay, and so the thing I want to explain to you here, as a really quick overview, is what we need to know is the equilibrium vapor pressure, right, of this droplet. And then the PI would just be the water vapor pressure of the environment, depending on, how much water vapor we have in any given time, any given location, which can be quite variable, right? Water vapor is one of these very variable gases in the atmosphere. Okay, and so equilibrium vapor pressure, there's several steps to this, how we should think of this, right? So the first thing would be to think about equilibrium vapor pressure over a flat surface of pure water, right? So think about now going away from our droplets. We have a little bucket, a little container with water. And so what happens here is that some molecules at the surface here, they have enough kinetic energy that they are able to break free from their friends, and they fill up this space above the surface, and others, they come back, right? So we have eventually, there will be an equilibrium of these flux going out and the flux coming back of water vapor or water molecules. And when that equilibrium is established, that pressure would be equilibrium vapor pressure, right? So you might have like, for example, this glass of water. So here's my demo. It looks like nothing is happening, right? But even in equilibrium, there's a lot happening, right? There's always water molecules breaking free, and then there are water molecules coming back. So it's a dynamic equilibrium, right? And if that level here is going down, we would call this evaporation. If it's going up, we would call it condensation, right? And if it doesn't change, then it's an equilibrium. And so now tell me, this equilibrium vapor pressure, actually I wrote it down, so I shouldn't have written the whole sentence, but this equilibrium vapor pressure is just a function of temperature, right? And it's given by the Clausius-Clapeyron equation. Everyone on board with that? Okay. Yeah, so Clausius-Clapeyron equation, and it's actually a very strong function of temperature. So if this is temperature, I'm not drawing a size distribution now for a change, temperature, and here is our equilibrium vapor pressure as a function of temperature. Let's call this here 0 degrees Celsius. It's an exponential function, right? A very strong function of temperature. And then what you know as relative humidity, when you look at the weather app and it reports relative humidity is just the ratio of the real, what am I going to call this? The real vapor pressure in the air divided by the equilibrium vapor pressure at that temperature that we have at that time. And if that gets to high numbers, like 70, 80%, we know it's muggy and we feel uncomfortable, right? So we know this from our daily life. Okay, so that's the Clausius-Clapeyron equation. It's just a function of temperature, nothing else. And it tells you what the equilibrium vapor pressure is at that temperature. Now, with our little aerosol droplets that are a solution of ammonium sulfate, nitrate, maybe some organics and water, we have to adapt this a little bit. Why? Well, first of all, it's not a flat surface, it's a curved surface, right? And second, it's not pure water, but it has something dissolved in it, which can depend on what the seed aerosol was. Okay, so the curved surface effect, to account for this, so that's essentially the Kelvin effect, right? And to account for this, that's fairly easy. So the water, my notation is getting a little wonky here. Let's call this PW. Our PW is a function now of the droplet diameter. It's the, I should say droplet diameter and temperature. It's the equilibrium that we know from our Clausius-Clapeyron equation. And then, do you know what happens? What do we have to do? We have to now multiply with a term. Does anyone know what that, like roughly speaking, what that term contains? No, what the term? We multiply by an exponential. So if you have a droplet, a small droplet that has a large curvature, to keep that in equilibrium, you need to increase the surrounding vapor pressure, right? So if you have a droplet and you think, oh, what's the equilibrium vapor pressure? Let's calculate it with Clausius-Clapeyron here. And you expose this droplet to exactly that vapor pressure, that droplet would actually evaporate. It's not in equilibrium, right? And the smaller the droplet is, the higher you need to make the surrounding vapor pressure to keep it in equilibrium. Okay, and so the term here is, let's move this over. So M sub W is the molecular weight of water. Sigma is the surface tension. And then we divide by RT, density of water, and importantly, the diameter. And so I think I mentioned this yesterday when we talked about aerosol and clouds in the first place. So if you just have water vapor and you want to make a cloud droplet, to form a cluster of water molecules that stays together, that is stable, and let's assume you don't have any aerosols around, you need a huge, huge water vapor pressure, right, to overcome the Kelvin effect. This is exactly why. And so this is why now the aerosols really help, because they provide like a surface already. And so you get a little head start, right? And so you don't need such a high vapor pressure to get going. Okay, and so the other thing that happens here is that, that the Kelvin effect increases the equilibrium vapor pressure that you need in this way. And then parallel to this, at the same time, we have an effect called the Raoult effect. And so that is because you have a solution, right? We have not pure water. And that effect is just the opposite. It actually decreases the equilibrium vapor pressure. So if you look at this example here, where we have our bucket or our cup of water, and the baseline is pure water, you use the Clausius-Clapeyron equation to figure out what's the equilibrium vapor pressure. If you dissolve a salt in there, that equilibrium vapor pressure would actually decrease, right? And now we combine it with a surface that is curved, and we have the Kelvin effect at the same time, which increases the equilibrium vapor pressure. And so then both things work at once. And the equation that we use, this is after a little bit of linearizing, so that the exponential goes away. I just give you like the end result here. But that is a very important concept in aerosol science. And if you are interested in how they impact clouds and how cloud formation works, right? So aerosol cloud interactions, I would say that's a very foundational figure. And it's called, after the person who developed this was way back in the 1930s. The name was Köhler. So these are the Köhler curves. And so this whole thing is called Köhler theory. The equilibrium that establishes for an aerosol particle that is exposed to a certain relative humidity. And so let me just explain how that works, because it's yet another type of plot that you get exposed to here. One thing that we often work with is it's called supersaturation, right? So that is the saturation above 100% relative humidity. And that relative humidity is always with respect to a flat surface of pure water, right? And so if you are above this line here, then you are supersaturated, so higher than 100%. If you are below, then you are subsaturated, so lower than 100%. And then on the x-axis is the wet diameter. So it's the diameter of the whole aerosol plus water, little droplet. And then we have different lines here. Let's focus on the solid lines, which is for sodium chloride. So that would be like your sea salt, right? Let's look at this line right here. Oops. And this line tells us what the equilibrium vapor pressure is given the fact that we have a tiny little sea salt particle involved, right? So the sea salt portion of this droplet is 0.05 micrometer in diameter. So you could convert this to how much mass of sea salt this is, so very little. And then the x-axis, the wet diameter, changes because you are adding more and more water, right? But you always keep the amount of sea salt the same for this one curve. And then for the next one, we take more sea salt, so we use 0.1 micron sea salt particle, and down here it's a 0.5 micrometer sea salt particle. Okay, and so then what does this tell us? So the right-hand side here, this is really interesting. If you go to the right-hand side, how do I indicate this? Here. So you basically see as the particle gets smaller, the wet diameter decreases, right? You need a higher and higher and higher supersaturation to keep this droplet in equilibrium. And so that's your Kelvin effect, right? And if we didn't have any NaCl in there, sea salt dissolved, that curve would just continue up, right? It would have like a singularity as you go to diameter towards 0. So the pure water version of this, would continue like this. So only Kelvin effect. As diameter, the wet diameter goes to 0, the supersaturation that you need. For equilibrium goes to infinity. But if you actually have a little sodium chloride or whatever ammonium sulfate dissolved in your water droplet, that doesn't happen. And so instead what happens is it turns around and forms the other branch here of our Kohler curve. It goes down. Eventually, as we go to smaller and smaller diameters here, the supersaturation becomes negative. So we go to subsaturated conditions, right? And so this point here, this is all equilibrium, right? So this point here is also really interesting because, and now this has to do with, stable and unstable equilibria. This happens in other fields or applications as well, and so this is one application. So let's go through this a little bit. So what happens is if you have, let's say, you start out here, you are subsaturated, just below 100% relative humidity, and you have your sodium chloride particle in equilibrium. And what always happens is that a few water molecules are joining the droplet and are going away from the droplet again, right? And so let's just focus on the situation. Let's say there are a few water molecules joining the droplet, right? So we are getting a little bit bigger. So let's start here. Oops. And a few water molecules are joining. So we are getting a little bit bigger. We move over here. So now, if the environment, now this particle to be in equilibrium would actually need a supersaturation, but the environment hasn't changed, right? So a few molecules joined, the equilibrium the equilibrium size has changed, but what happens if the environment didn't change? It falls back, right? They evaporate again, and so this droplet actually doesn't change. It's in a stable equilibrium. So my point is, if we impose a perturbation, that perturbation gets dampened, right? Because the equilibrium curve has this shape. Now let's look at the other branch. Let's look over here. Again, same example. We have this particle, it has this size. It's in equilibrium initially. And now let's have it a few water molecules joining. So it becomes a tiny little bit bigger over here. And the environment hasn't changed, right? The environment still has the same amount of moisture. Now that's a very different situation because now by adding a few water molecules and making this particle a tiny little bit bigger, its new equilibrium saturation is actually lower, right? And so if the environment hasn't changed, this particle now will feel supersaturated suddenly, right? And so that branch is an example of an unstable equilibrium. So we go from a stable equilibrium over here to an unstable equilibrium over here. And then there's this point, this maximum point here, a bifurcation, but we call this point is a very important point in aerosol science. That is called the critical diameter. And the corresponding supersaturation is called the critical supersaturation. And so you can see, and what the language that we use is if a if an aerosol particle is exposed to its critical supersaturation or higher, it activates, right? It becomes a cloud droplet. It changes from being a haze droplet in its stable equilibrium to be a cloud droplet in an unstable equilibrium. And if the environmental saturation doesn't change, it will actually grow very quickly, right? So you have your haze particle, it doesn't do much, but once you hit the critical supersaturation, you get this very quick growth of water droplets into cloud droplets. And then we call them cloud droplets, right? It's like a nomenclature choice. But essentially, it's just aerosol particles with a lot of water on them, right? So, yeah. And what else did I want to say? Stable and unstable equilibrium. Oh, yeah. So if you start out with a very small sodium chloride particle, right? You see the critical supersaturation is very high. If you make this sodium chloride particle bigger and bigger, the critical supersaturation drops, right? Where this change happens from stable to unstable growth. And here for 0.5, it's barely visible above 0 supersaturation, meaning 100%. So bigger, this is what I said at the very beginning, bigger particles are easier to activate to become cloud droplets compared to smaller particles. So this is basically proving this now mathematically. And if you have a really tiny particle, you need a huge supersaturation. And so these are salts, which are very, hygroscopic and easy to make clouds out of them. If you make this curve for one of your combustion soot particles, it would go way, 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 way up higher, right? And so given that in your aerosol population, you have always, soot and other particles, the other particles will activate first, right? And they will grab all the water, and then they suppress the environmental saturation. And this is why the soot particles, unless they have any coatings, hygroscopic coatings, that's why they are left behind and not get into a cloud and not get removed by wet deposition, right? Okay, that's that. I think I've had, oh yeah, so the other thing, this is now when it becomes more relevant for, or where the meteorology comes in, right? So what determines what supersaturation you have, right? And so that is determined by how do we make supersaturations in the atmosphere. We have to cool our air parcel, and cooling works either by lifting the air parcels up, or sometimes you can also stay at one level, let's say the surface, during the nighttime. It just can cool without moving, right? You just have radiative cooling. So there are different mechanisms of cooling. That's how you create supersaturations. And then you also have the loss, and the loss is because the particles take up the water and the droplets are growing, right? So you can formulate, we won't go through the details now, but like a ds by dt, so S being the supersaturation, there's also a production and a loss. And the production is from cooling our air parcel with the aerosols in there. And that can come from rising air or radiative cooling. And the loss would be aerosols take up water, become cloud droplets, and those cloud droplets grow. And so, you know, if you have a very gentle cloud, like more, you know, like a stratus cloud. Now I shouldn't probably get into all of those details, but the supersaturation that you produce are very low because you're not having strong updrafts. If you have like a thunderstorm cloud with really strong updrafts, if you fly through clouds, you know this, right? Clouds are very bumpy. Then you create high supersaturations. So this is where all the meteorology comes in. Okay, so that was Kohler theory. Stable and unstable, yeah?
What do you think is going to happen to, like, if combustion's using more hydrogenated fuels, like pure hydrogen or ammonia, they produce a lot more water. So how's that going to affect, like, would you be able to be supersaturated more easily in the atmosphere if we're outputting more water vapor?
That's a really good question. I think, so what you're saying is you're producing water vapor in the exhaust? Yeah.
More than you, like we always produce water
Mm-hmm.
but if you switch to something like hydrogen or ammonia, you're going to produce
Even more, way more. Yeah, so then whatever comes out, the initial exhaust, I would say, is at quite high relative humidities, right? And the particles, are you also emitting particles still? No. It depends. Yeah, so initially, if there are any particles, they probably will contain water quite a bit. But I think with the mixing of the air, so, you know, there's a lot of air around, right? And that is at a different moisture. And if it's high up, are you talking about what kind of, like, planes or?
Yeah, like planes.
Planes are often, that air is often quite dry, right? And so then you would, the droplets would evaporate. They would be there initially, and then as you have the mixing going on, they would evaporate and then eventually dry out. How long that takes, I don't know. That one could calculate that, right? You could probably calculate it now with all your equations. Yeah, but yeah, that's an interesting example where you change the initial conditions, right? I think I was talking to somebody else who was asking the question, so what, from the combustion community, what can we provide, right? And so the thing that is really valuable to people like me and other people who do modeling of aerosols in the atmosphere is you are providing the initial conditions, right? For us, it's the initial conditions. For you, it's probably the end point, like after you're done with your combustion process and it gets out. This is our beginning, our starting point. And if the initial conditions are wrong, what happens to your simulation? It's bad news, right? We are doomed from the beginning. And so knowing the properties, I've been working with people who do these experiments for cars. What comes out of a car, right? Like, it depends from car to car, of course, and or from model to model and how old the model is. So it's a lot of detail, but at the end of the day, we really need to simplify, right? Like coming up with some representative size distributions, composition profiles, to make it tractable. And so that is really, I think, where our communities come together and can use the results, all the detailed thing, what's going on in the engine. At the end of the day, it produces something, and that something is what we need to put into our models to propagate it forwards and calculate the impacts. So it's a very important joint right there. Mm-hmm. All right. Since we were talking about condensation and coagulation, that's another thing to keep in mind. And the growing, so this is why this slide comes. I was trying to remember, why am I showing this slide now? Growing aerosols to cloud droplets, right? And so once they are a cloud droplet, they really efficiently this is what this climate relevance means, right? They are scattering the light back, reflecting the light back into space. So suddenly they are relevant for climate. If you have a really tiny particle, like 10 to the minus 9, these would be the freshly nucleated one, what we talked about yesterday, right? The sulfuric acid particles, when they are tiny. So at that point, they are not climate relevant, right? They can't become a CCN. The critical supersaturation is huge. It wouldn't happen, right? So somehow they have to get over the line here to grow, several orders of magnitudes, in fact. And once they are that range, like 0.1, this is 0.1 micron, right? 100 nanometer. Then we can talk about, okay, they could become a cloud droplet right here. But on its way, having these tons of tiny, freshly nucleated particles, they are intercepted by the coagulators, right? They scavenge them up, what you drew when you drew the size distribution right now. So they are not going to make it. They are scavenged, right, by the bigger particles. So it's not really, there's this issue, right, of if you are a nucleation person who studies nucleation, the question that they are asking is, of my tons of tiny particles that I'm producing in each of these nucleation bursts, what is the fraction that survives? And so you need to know something about how many other particles are there, right? And so what is the size of these other particles to simulate that survival process until you get to your CCN concentration. So that's the competition between condensation and coagulation. Okay, how are we doing with time? When did we start? I think we are almost done, right, with the second hour? Okay, so it's a different topic now starting, so let's take a break right now.